Welcome, dear listener, to a tranquil journey through the cosmos, where we'll explore one of the universe's most magnificent transformations. Tonight, as you settle into comfort, allowing your breathing to slow and deepen, releasing the tensions of the day, letting your muscles soften and your mind quiet, we're going to contemplate something both ancient and immediate, something vast and intimately personal. We're going to witness the death of stars, those brilliant lights scattered across the night sky, and in doing so, we might find unexpected peace with the endings in our own lives. Feel yourself sinking deeper into rest with each breath. Notice the gentle rise and fall of your chest, the quiet rhythm that connects you to all living things, the same rhythm that echoes through the universe in pulses of stellar light and waves of cosmic expansion. You are safe here. You are held by the same gravity that shapes galaxies and guides planets in their orbits. And tonight, in this peaceful space, we're going to explore one of nature's greatest lessons about transformation, change, and the beauty of endings. Before we begin this cosmic meditation, if you find value in these explorations where science meets serenity, I invite you to subscribe to Gentle Sleep ASMR. Your support allows us to continue creating these peaceful journeys where the mysteries of the universe become gentle companions for your rest. Each video we craft is designed to help you drift into sleep while expanding your understanding of the cosmos and your place within it. Take another breath with me now, letting it flow in slowly, filling your lungs completely, then releasing it with a gentle sigh. Feel yourself settling. The universe has been ending and beginning for 13.8 billion years, cycling through transformations beyond counting. And tonight, you're part of that eternal rhythm. There is something profoundly comforting in knowing that transformation, not permanence, is the true nature of everything that exists. Nothing stays the same forever. Not the mightiest star, not the vastest galaxy. And yet nothing is ever truly lost. Everything transforms, continues, becomes something new. When you look up at the night sky on a clear evening, away from the city lights that wash out the stars, you're gazing into a vast memorial garden, a cosmic cemetery that's also a nursery. Every point of light you see twinkling in the darkness is a star, and every star is either preparing for its end, currently in the process of dying, or already dead. That star you're seeing might have exploded 1,000 years ago, or 10,000, or 1,000,000, but its light is only now completing its journey to your retina, to your consciousness, to your wonder. This might sound melancholic at first, this idea that we're looking at a sky full of endings, but there's a strange, deep peace in it when you let it settle into your awareness. The stars teach us that endings are not failures. They're not aberrations in the cosmic order, not mistakes or tragedies to be avoided at all costs. They're essential, beautiful, creative acts. They're necessary. Without stellar death, without these cosmic endings, nothing interesting could exist. Not planets, not oceans, not forests, not you. Tonight, we're going to walk together through the life and death of massive stars. Those celestial giants at least 8 times more massive than our own Sunday. Sometimes 10 times larger, 20 times, 50 times, even 100 times more massive. Well, Witness their formation in clouds of gas and dust, their long, stable lives burning hydrogen in their cores, their gradual evolution through different burning stages, their final days before collapse, and then their spectacular deaths in supernova explosions. Briefly outshine in galaxies. Well, explore what remains afterward, the strange remnants they leave behind, neutron stars and black holes, and expanding clouds of enriched gas. But this isn't just a story about distant balls of fusion-powered plasma. It's not merely an astronomy lesson delivered in soothing tones. It's a story about transformation, about the psychology of endings, about what it means when something that seemed permanent, solid, eternal, reveals itself to be temporary after all. It's about how we cope with change, how we process loss, how we find meaning in the midst of transformation. And perhaps most importantly, it's about recognizing that we are intimately, physically connected to these stellar deaths in ways that make them deeply, personally relevant. You see, we are made of stars. This isn't poetry, though it certainly sounds poetic when you first hear it. This isn't metaphor or flowery language or some new age mysticism. It's literal, verifiable, scientific truth, confirmed by decades of careful observation and rigorous analysis. The atoms in your body, every single one heavier than hydrogen, every atom of carbon and nitrogen and oxygen and calcium and iron, were forged inside dying stars billions of years ago, then scattered across space in supernova explosions, then gathered into new clouds of gas and dust, then incorporated into our Sunday and the planets that formed around it, and eventually, through the long processes of geology and chemistry and biology, arranged into the pattern that is you. The calcium in your bones, giving them strength and structure, was created when a massive star's core collapsed and rebounded in a supernova explosion. The iron in your blood, carrying oxygen to every cell in your body, enabling your very metabolism and consciousness, was synthesized in the final seconds before that same supernova when silicon fused into iron in the star's core. The oxygen you're breathing right now, pulling into your lungs with each gentle breath, was fused in the core of a red giant star that swelled to enormous size before dying, that no longer exists as a star, but continues through its scattered elements. Every breath connects you to stellar death. Every heartbeat pumps iron created in supernovae through your veins. Every thought you think occurs in neurons built from carbon and nitrogen and phosphorus, all elements created in and dispersed by dying stars. You are not separate from these cosmic processes we're exploring tonight. You are their direct result, their continuation, their legacy made conscious and aware. This means that you, settling here into rest, listening to these words, contemplating the nature of endings, are a continuation of stellar death. You are what stars become when they die, and their elements recombine in new patterns. Their endings made your beginning possible. The deaths of countless massive stars over billions of years created the chemical richness necessary for planets and life. Without those deaths, those violent transformations, those scatterings of created elements across the cosmos, you could not exist. You are proof that death is creative, that endings enable beginnings, that transformation is the engine of cosmic evolution. The poet and scientist Carl Sagan called us star stuff, pondering the stars, and he was profoundly right. We are the universe's way of looking at itself, of understanding its own processes of transformation and renewal, of finding meaning and beauty in its own existence. And that's what we're doing tonight as we journey through stellar death. We're not just learning about distant astronomical phenomena, we're exploring ourselves, our own nature, our own connection to the vast cycles of cosmic change. So as we journey through stellar death together, we're also exploring the emotional and spiritual dimensions of endings, the psychological challenge of letting go and transforming, of accepting that nothing lasts forever, while recognizing that nothing is ever truly lost. Stars don't fight their deaths. They follow the inexorable laws of physics, moving from one state to another, creating beauty and possibility in the process, enriching the universe through their transformation. Perhaps Therese's wisdom in that for us too. We who struggle so much with change and loss and the passage of time. Let's begin at the beginning, or at least at the long, stable middle that precedes every ending. Imagine a region of space, vast beyond human comprehension, filled with clouds of gas and dust. These stellar nurseries, called nebulae, can be hundreds of light years across. To give you a sense of scale, a light year is the distance light travels in 1 year, moving at 300,000 kilometers per second econd, which equals about 9.5 trillion kilometers. A nebula hundreds of light years across contains enough material to make millions or even billions of stars, like our Sunday. These clouds are beautiful when photographed by powerful telescopes like Hubble or the James Webb Space Telescope. The Eagle Nebula, with its famous pillars of creation, towering columns of gas and dust, 7 light years tall, where new stars are being born. The Orion Nebula, visible to the naked eye as a fuzzy patch in Orion's sword, a stellar nursery only 1,300 light years away, where thousands of stars are currently forming. The Carina Nebula, home to some of the most massive and luminous stars in our galaxy. Stars that will live fast and die young in spectacular supernovae. Within these vast clouds, in certain dense pockets, where the gas and dust have accumulated more thickly than in surrounding regions, gravity begins its patient work. Atoms attract atoms. Dust grains clump with dust grains. The attraction is weak at first, barely noticeable, but gravity is relentless. It never sleeps, never stops pulling, never gives up. Over tens of thousands of years, then hundreds of thousands, then millions, these accumulations grow denser and more massive. As the cloud contracts under its own gravity, it begins to spin, conserving angular momentum, like a figure skater pulling in their arms to spin faster. The rotation flattens the cloud into a disk, with most of the mass falling toward the center. This central condensation grows hotter as it contracts, the gravitational potential energy converting to thermal energy. The atoms are moving faster, colliding more violently, and the temperature climbs from the frigid near absolute zero cold of interstellar space to tens of thousands of degrees. Eventually, after millions of years of patient accumulation and contraction, if enough mass has collected in the center, something remarkable happens. The temperature and pressure at the core of this collapsing cloud becomes so intense that hydrogen nuclei normally repelling each other due to their positive electrical charges are forced close enough together that the strong nuclear force can bind them. Hydrogen begins to fuse into helium, releasing tremendous energy in the process. Energy that Einstein's famous equation tells us comes from converting a tiny amount of mass directly into energy. A star is born, not in an instant, not in a sudden flash, but through a gradual accumulation of conditions that suddenly, after eons of preparation, cross a critical threshold. One moment rears a dark protostar, a condensation of gas heated by gravitational contraction, but not yet sustaining fusion. The next moment, fusion ignites and Therese light. The star begins to shine, pouring energy out into space, pushing back against the gravity that created it, achieving the delicate balance that will sustain it for millions or billions of years. For massive stars, those we're focusing on tonight, stars at least 8 times the mass of our Sunday, this ignition marks the beginning of a life that will be cosmically brief. While stars like our Sunday can shine steadily for 10 billion years, massive stars burn through their fuel much more quickly, living fast and dying young. A star 8 times the Sun's mass might last 40 million years. A star 20 times the Sun's mass, only 10 million years. A star of 50 solar masses might last just a few million years, and the most massive stars, 100 times the Sun's mass or more, might exhaust their fuel in only 1 or 2 million years. That might seem like a long time to us, with our decades of human life, our centuries of recorded history, our thousands of years of civilization. But in cosmic terms, it's the blink of an eye, a brief candle flame in the long darkness. The universe is 13.8 billion years old. Massive stars live for less than 1% of that time, sometimes less than 1/10 of 1%. They're the meteors of the stellar world, brilliant but fleeting, burning bright and fast before exploding in spectacular fashion. But for most of their existence, even these cosmic sprinters experience a kind of peace, a dynamic equilibrium. The star enters what astronomers call the main sequence, a long period of stability where hydrogen fuses to helium in the core. This fusion, this joining together of 4 hydrogen nuclei to create one helium nucleus, releases energy according to Einstein's equation. The energy created by millions of these fusion reactions every second generates heat and radiation that creates an outward pressure, pushing against the star's own gravity. Meanwhile, the star's gravity pulls everything inward, trying to compress the star further. These two forces, the outward pressure from fusion and the inward pull of gravity, balance each other precisely. The star neither collapses nor explodes. It exists in equilibrium, a nuclear furnace contained by its own weight, shining steadily into space, maintaining its size and temperature for millions of years. There is something deeply reassuring about this balance, isn't there? The star exists in a state of dynamic equilibrium, where powerful opposing forces perfectly counteract each other. It's not static. Inside the star there is constant activity, constant motion, constant transformation, as hydrogen converts to helium. But the overall structure remains stable, predictable, reliable. Perhaps you've experienced periods like this in your own life. Times when everything seemed to work, when the various forces pulling at you somehow balanced out, when you could simply exist, simply be yourself, simply shine with whatever light was yours to give. These stable periods can last a very long time. They can feel permanent, eternal, as though they'll continue forever. The star shines, day after day, year after year, millennium after millennium, seemingly unchanging. But nothing lasts forever in this universe, not even the stars. The hydrogen fuel in the core, vast as it is not infinite. Slowly, steadily, inexorably, the star converts hydrogen to helium through fusion reactions. And as the hydrogen depletes, the core begins to change. The helium that's created doesn't fuse at the temperatures and pressures of the main sequence. It accumulates in the core like ash from a fire. As more and more helium accumulates, the region of active hydrogen fusion moves outward into a shell surrounding the helium core. This is the first sign that transformation is approaching, the first indication that the long, stable period is coming to an end. Though from the outside, the star might still appear much the same to a distant observer. Inside, though, everything is beginning to shift. The helium core, no longer supported by fusion energy, begins to contract under its own weight. As it contracts, gravitational potential energy converts to heat, and the core temperature rises. The rising temperature heats the hydrogen, burning shell around the core, causing it to fuse faster, releasing more energy. This extra energy causes the star's outer envelope to expand dramatically. The star swells, growing larger and larger, its outer layers moving farther from the hot core. As these outer layers expand, they cool, and the star's surface temperature drops. The star's color shifts from blue, white, or yellow to orange or red. The star has become what astronomers call a red giant, or for the most massive stars, a red supergiant. Its luminosity increases enormously because even though the surface is cooler, the star's total surface area has increased by factors of hundreds or thousands. You can see one of these red supergiants with your own eyes in the winter night sky. Betelgeuse, marking the shoulder of Orion the Hunter, that distinctive reddish star in one of the most recognizable constellations, is in precisely this phase of its life. It's a star in its terminal stage, having exhausted the hydrogen in its core and expanded to a size almost 1,000 times larger than our Sunday. If you placed Betelgeuse where our Sunday is, its outer layers would extend past the orbit of Mars, possibly reaching Jupiter. Earth would be deep inside the star, vaporized. Betelgeuse will explode as a supernova sometime in the next 100,000 years. In cosmic terms, that means it could happen tomorrow. It could happen while you're listening to this. Or it could happen 10,000 years from now, or 50,000. We simply don't know. The star is clearly unstable, changing in brightness irregularly, pulsating, losing mass through powerful stellar winds. When it does finally explode, it will be bright enough to see during the day, a brilliant point of light visible in the daytime sky for weeks or months, a star death observable in broad daylight from Earth, somewhere between 500 and 700 light-years away. There's a strange beauty in this red giant phase. Don't you think? The star is dying. Yes, clearly in its final stage of life. But it's also glowing with a softer, deeper, more luminous light than it ever did during its main sequence phase. It's expanded, become more diffuse, more generous with its energy. The star is no longer the tight, hot, fierce fusion reactor it was during its youth. It's become something larger, cooler, but also more magnificent in its way. A bloated giant casting red light across the cosmos. And the star is already beginning the process of giving back, of releasing what it's created during its lifetime. Red giants and supergiants shed material into space through powerful stellar winds, streams of particles flowing outward from the star's surface at speeds of tens or hundreds of kilometers per second econd. These winds can carry away substantial amounts of mass over thousands or millions of years, enriching the surrounding interstellar medium with heavier elements created in the star's core during its lifetime. Think about that for a moment. The star doesn't hoard everything until the very end, doesn't hold onto its creations until forced to release them in the final explosive moment. It begins letting go early, releasing material in a steady wind, like leaves falling from a tree in autumn, allowing parts of itself to drift away and become something else. Teresa lesson there, perhaps, about not waiting until we're forced to let go, about the grace of gradual release, about sharing what we've created while we still can. For the massive star, though, this red supergiant phase is just the beginning of a cascade of increasingly rapid transformations. The helium accumulating in the core eventually becomes dense and hot enough to ignite its own fusion at temperatures around 100 million degrees Kelvin. 3 helium nuclei can fuse together in a reaction called the triple alpha process, creating carbon. Further, helium fusion creates oxygen. The star now has a carbon-oxygen core surrounded by a helium-burning shell, which is surrounded by a hydrogen-burning shell, all enclosed in the star's vast extended envelope. But the helium fuel, like the hydrogen before it, is not infinite. When the helium in the core is exhausted, the core contracts again, heats up again, and if the star is massive enough, carbon begins to fuse at temperatures around 500 million degrees, creating neon, sodium, and magnesium. Then the carbon is exhausted, and neon begins to fuse, creating oxygen and magnesium. Then oxygen fuses, creating silicon, sulfur, and other elements near silicon in the periodic table. Then silicon fuses, creating elements around iron. Each burning stage happens more quickly than the last. This is crucial to understand. The star is accelerating toward its end, each transformation coming faster and faster, like a ball rolling down a hill that gets steeper and steeper. Hydrogen fusion. Helium fusion might last hundreds of thousands of years. Carbon burning, just a few hundred years. Neon burning, about a year. Oxygen burning, mere months, perhaps only 6 months to a year. Silicon burning, the final stage before catastrophe, lasts only days, perhaps just a week or two. The star is building layers like an onion now, with different elements fusing in concentric shells around the core. At the very center, silicon fuses into iron, nickel, and cobalt, the elements around iron in the periodic table. Surrounding that is a shell where oxygen is fusing into silicon. Outside that, a shell of neon burning, then carbon burning, then helium burning, then hydrogen burning, all happening simultaneously in different shells at different temperatures and densities. The star has become a cosmic onion. And this is where the star's fate is sealed. Iron is the most stable element in the universe. It has the highest binding energy per nucleon of any element. This means that fusing iron into heavier elements doesn't release energy the way fusing lighter elements does. In fact, it requires energy. It's an endothermic reaction, consuming energy rather than producing it. When the core fills with iron, when this ash of silicon burning accumulates at the star's center, the star has reached a dead end. There is no more nuclear fuel that can burn and provide the outward pressure to counteract gravity. The core of iron grows, fed by the silicon fusion happening in the shell around it, accumulating more and more mass with each passing hour. All of this is happening in a space smaller than Earth. This iron core growing at the heart of a star that might be hundreds of millions of kilometers across. A star whose outer layers might extend farther than the orbit of Mars, or even Jupiter. But at the very center, in a region you could fit inside Earth's orbit around the Sunday, an iron core is accumulating, growing heavier, approaching a critical threshold. Recent observations have given us unprecedented glimpses of stars in these final stages, revealing that stellar death can be even more complex and violent than we previously imagined. A supernova designated SN 2023 FIQ, observed by astronomers using the Very Large Array Radio Telescope in New Mexico, made history as the first type Ibn supernova ever detected in radio wavelengths. This observation revealed something remarkable about the star's final years before explosion. The radio signals showed that the star had undergone dramatic mass loss in the 5 years immediately before it exploded. The star was shedding material at an astonishing rate, up to 0.4% of the sun's entire mass every year, driven by what scientists believe was either the gravitational influence of a companion star or by massive pre-supernova eruptions. The star was literally coming apart before the final explosion, releasing vast quantities of helium, rich material into the space immediately surrounding it. When the supernova finally detonated, the explosion plowed into this cocoon of previously ejected material, creating intense radio emissions that astronomers could detect across the vast distance separating us from this dying star. This discovery showed us that the final years or decades of a massive star's life can be turbulent, chaotic, marked by outbursts and instabilities, as the star sheds layers of its outer envelope in increasingly violent episodes. There is something deeply human about this, isn't there? The turbulence before transformation, the instability before the final change, the shedding of what we've been, sometimes violently, sometimes through a steady erosion we can barely perceive, preparing for a transformation we might not survive in our current form. These stars, in their final years or final days, are undergoing profound change, and it's not always graceful or peaceful or gentle. It's often chaotic, uncertain, marked by outbursts and dramatic shifts in behavior. If you've ever stood on the edge of a major life transition, if you felt the ground shifting beneath you as something that seemed permanent, solid, reliable, revealed itself to be temporary after all, you know this feeling. The job that defined you, that gave structure to your days and identity to your sense of self, suddenly ends, leaving you adrift. The relationship that anchored you, that you built your life around, transforms or dissolves, and you're forced to reimagine your future. The health you took for granted fails, and you must learn to live in a body that no longer does what you expect. The future you envisioned becomes impossible, and you're forced to envision something entirely new. These moments, these transitions, can feel catastrophic. The word itself comes from the Greek for overturning, for a sudden turning point. And that's exactly what they are. Everything that seemed stable overturns. The old patterns no longer work. The familiar structures collapse, and we're left in chaos, uncertainty, turbulence, not knowing what comes next, or who will be on the other side of this transformation. And perhaps these moments are, in their way, personal supernovae, stellar deaths playing out in the theater of a human life. They're endings that will leave us fundamentally changed, transformed into something we cannot yet imagine, scattered and reconstituted in new patterns. They're frightening, they're painful. They feel like death, like endings, like the collapse of everything we've built and become. But let's stay with our star for now, in these final moments before the collapse that will change everything. The iron core sits at the center of the star, growing heavier with each passing hour as silicon fusion in the surrounding shell continues to add more iron ash. The star's outer layers continue their own fusion reactions. The onion, skin shells of silicon burning, oxygen burning, neon burning, carbon burning, helium burning, hydrogen burning, all operating at different rates, all contributing to the iron core that will ultimately doom the star. The iron core is supported against gravitational collapse by electron degeneracy pressure, a quantum mechanical effect that prevents electrons from occupying the same quantum state. The electrons in the iron nuclei are packed together as tightly as the Pauli exclusion principle allows, creating an outward pressure that, for now, balances the inward pull of gravity. The core is in a kind of equilibrium, but it's a precarious equilibrium, unstable, ready to collapse at any moment. The core continues to grow. 1.2 solar masses, 1.3, 1.4, and at approximately 1.4 times the mass of the Sunday, the threshold known as the Chandrasekhar limit. Electron degeneracy pressure can no longer support the core's weight. The limit is named after Subramanian Chandrasekhar, who calculated this critical mass in the 1930s while still a graduate student, work that would eventually win him the Nobel Prize in Physics. When the iron core exceeds the Chandrasekhar limit, everything that has been building for millions of years comes to a head in less than a second. The core, having lost the support of electron degeneracy pressure, begins to collapse, not slowly, not gradually, but catastrophically, imploding at speeds that approach 1/4 the speed of light. In a fraction of a heartbeat, in less time than it takes you to blink, the core of the star, an object roughly the size of Earth containing 1.4 times the mass of the Sunday, compresses down to something the size of a city, perhaps only 20 or 30 kilometers across. This is where we'll pause for now, at the precipice of catastrophe, at the moment before everything changes. In the next part of our journey, we'll witness the collapse and explosion itself, the supernova that scatters the star's elements across space and leaves behind a neutron star or black hole. We'll explore what these explosions create and what they leave behind. But for now, rest here with the knowledge that even in these final moments, even as the iron core grows and the star approaches its end, there is beauty, complexity, a kind of terrible magnificence in the processes at work. The collapse begins. In less than 1 second, everything changes. The iron core that has been growing at the star's center, fed by silicon fusion in the shell surrounding it, finally exceeds the Chandrasekhar limit. The electron degeneracy pressure that has been supporting the core against its own gravity, that quantum mechanical force preventing electrons from being squeezed too close together, suddenly fails. It's not a gradual failure, not a slow weakening. It's catastrophic, instantaneous, total. The core, an object roughly the size of Earth containing 1.4 times the mass of the Sunday, begins to implode. Implode is the right word here, not collapse. This isn't a gentle settling or a gradual compression. This is a violent runaway contraction, happening at speeds that challenge comprehension. The outer parts of the core are falling inward at 70,000 kilometers per second econd, roughly 1/4 the speed of light. In a single second, material travels a distance equal to twice the distance between Earth and the Moon. Imagine if you could somehow watch this happen in slow motion, though even slow motion would show events unfolding faster than your mind could process. The core that took millions of years to build, that accumulated through patient nuclear fusion, that grew layer by layer as the star burned through its fuel, now collapses in less time than it takes you to snap your fingers. The density climbs exponentially. The temperature soars past 5 billion degrees Kelvin, then 10 billion, then higher still. At these temperatures, the very fabric of matter begins to change. The photons, the particles of light, carry so much energy that they can tear apart atomic nuclei through a process called photodisintegration. The iron nuclei that marked the end of the star's fusion processes, the stable configuration of protons and neutrons that couldn't release energy through further fusion, are blasted back into helium nuclei and then into individual protons and neutrons. All the nuclear binding energy that was released when these elements were originally fused during the stars. Life is now consumed, absorbed back into the process of ripping them apart. This absorption of energy causes the core to cool slightly, at least in relative terms, and lose pressure. With less pressure, gravity pulls even harder, and the collapse accelerates further. It's a runaway process, a positive feedback loop with only one possible outcome. The star has crossed a threshold from which there is no return. There no pause button, no way to reverse course, no possibility of re-establishing equilibrium. The collapse must continue until something stops it, and that something lies ahead, at densities we can barely imagine. As the density climbs, electrons and protons are forced closer and closer together. Under normal circumstances, these particles repel each other. Electrons carry negative charge, protons carry positive charge, but they exist in separate domains, electrons orbiting at relatively vast distances from the tiny nucleus. But in the collapsing core, the distinction between nucleus and electron cloud disappears. Everything is crushed together, and at these extreme densities, it becomes energetically favorable for electrons and protons to merge. This is electron capture, a process where electrons are literally pushed into atomic nuclei and absorbed by protons, creating neutrons and releasing neutrinos. The neutrinos are elementary particles so weakly interacting that they can pass through light years of solid lead without touching anything. Under normal circumstances, neutrinos zip through matter as though it weren't there. But the collapsing core is producing neutrinos in such staggering numbers that even though each one barely interacts with normal matter, collectively they carry away enormous amounts of energy. In just a few seconds, the collapsing core produces more neutrinos than have been created in all the billions of years the star has been burning. These neutrinos stream outward, escaping from the core, carrying away 99% of the gravitational binding energy released by the collapse. The energy is almost incomprehensible. If we could somehow convert 1/10 of the star's mass directly into pure energy, according to Einstein's famous equation, energy equals mass times the speed of light squared. That's the amount of energy the neutrinos are carrying away. For a brief moment, lasting only seconds, the collapsing stellar core outshines in neutrinos all the stars in the observable universe combined. But we can't see this neutrino flash with our eyes. Neutrinos don't interact with our retinas. They pass right through us, through Earth, through everything. When SN 1987A exploded in the Large Magellanic Cloud, a satellite galaxy orbiting the Milky Way about 160,000 light-years away, neutrino detectors on Earth registered a burst of neutrinos arriving hours before the visible light reached us. These detectors, buried deep underground to shield them from cosmic rays and other interference, caught just a handful of neutrinos out of the countless trillions that passed through Earth. But that handful was enough to confirm the theoretical predictions about core collapse and to mark the birth of neutrino astronomy. The collapse continues, accelerating, compressing, heating. The core that was roughly the size of Earth is now the size of a large city, then a small city, then just a few tens of kilometers across. The material is packed together so tightly that you could fit the entire mass of the sundae into a sphere small enough to fit across a metropolitan area. The density approaches that of an atomic nucleus, approximately 400 million billion kilograms per cubic meter. To give you a sense of scale, a single teaspoon of this material would weigh about 1 billion tons on Earth, roughly as much as a mountain. At nuclear density, something remarkable happens. The neutrons themselves, now packed together as closely as the particles in an atomic nucleus, become degenerate. The same quantum mechanical principle that created electron degeneracy pressure. The Pauli exclusion principle, preventing identical particles from occupying the same quantum state, now operates on neutrons. The neutron degeneracy pressure is stronger than the electron degeneracy pressure that failed. It's strong enough, finally, to halt the collapse. The core rebounds. This is the critical moment, the instant when implosion becomes explosion. The inner core, compressed to nuclear density, resists further compression and bounces back like a spring that's been compressed to its limit. The outer layers of the core, still falling inward at tremendous velocity, slam into this rebounding inner core. It's like dropping a ball onto a hard floor. The ball compresses slightly on impact, then springs back, bouncing upward. But in this case, the ball is made of stellar material falling at 1/4 the speed of light, and the floor is an incompressible sphere of degenerate neutrons. The collision creates a shock wave, a moving wall of pressure and energy that begins propagating outward through the star's outer layers. This shock wave is the supernova explosion. It tears through the star at velocities approaching 10% the speed of light, 30,000 kilometers per second econd. Everything in its path is heated to billions of degrees, compressed to extreme densities, and accelerated to escape velocity. The shock front is not just a wave of pressure, it's a nuclear furnace moving through the star, and in this furnace, the final act of nucleosynthesis takes place. Elements heavier than iron, elements that cannot be created through normal stellar fusion, because fusing them consumes energy rather than releasing it, are forged in the extreme conditions of the shock wave. This is explosive nucleosynthesis, and it happens through rapid neutron capture, the R process. In the tremendous neutron flux created by the collapsing core, atomic nuclei are bombarded with neutron after neutron, capturing them faster than they can undergo radioactive decay. They build up into increasingly neutron-rich isotopes, becoming heavier and heavier, climbing up the periodic table. These neutron-rich nuclei are unstable, but before they can decay, they capture more neutrons, building even heavier nuclei. When the neutron flux finally ends as the shock wave passes, these super-heavy neutron-rich isotopes decay through a cascade of beta decays, transforming neutrons into protons and settling into stable configurations. This is how gold is made. Platinum, lead, uranium, thorium, all the elements heavier than iron that exist in nature are created primarily in these few seconds of violent transformation. Every gold wedding ring on Earth, every platinum catalyst in a car's exhaust system, every uranium fuel rod in a nuclear reactor, every lead weight and every thorium welding rod. All of these are the direct products of stellar death, created in shock waves of exploding stars billions of years ago. Think about that for a moment, as you settle deeper into rest. The ring you might be wearing, if you're wearing one, or the gold fillings in your teeth, or any gold jewelry you've ever seen. Each atom of gold was created in the unimaginable violence of a supernova explosion, then scattered into space, then gathered into the cloud that became our solar system, then incorporated into Earth, then mined from the ground, then crafted into its current form. That atom of gold has traveled billions of years and countless trillions of kilometers to end up where it is now. It's ancient beyond imagining, forged in fire hotter than the surface of any star, cooled in the depths of space, and now resting here with you. The shock wave continues outward, taking hours to traverse the vast distance from the core to the star's surface. The star might have a radius hundreds of millions of kilometers across, its outer layers extending farther than the orbit of Mars or even Jupiter. The shock wave must travel through all of this material, heating it, accelerating it, transforming it from a bound stellar atmosphere into an expanding cloud of debris moving at thousands of kilometers per second econd. When the shock wave finally reaches the star's surface and erupts into space, the star begins to shine with the light of the supernova. The luminosity climbs exponentially over a period of hours or days, increasing by factors of millions or billions. A star that might have been too faint to see with the naked eye from Earth suddenly becomes visible across half the universe. For a few weeks, this single dying star can outshine an entire galaxy of hundreds of billions of stars. If Betelgeuse exploded tonight, if that red supergiant in Orion's shoulder underwent core collapse and detonated, we would see the light reach Earth sometime between 500 and 700 years from now. Since that's how far away the star is and light takes that long to travel the distance. But from our perspective, it would appear as a new star suddenly blazing in the sky. At its peak, it would shine as bright as a half moon, bright enough to see clearly during the day, bright enough to read by at night. It would remain visible in daylight for weeks, possibly months. At night, it would cast shadows, illuminate clouds, change the appearance of the familiar constellations. The ancient Chinese astronomers who observed the supernova of 1050 4C called it a guest star, a temporary visitor to the fixed patterns of the heavens. They recorded it meticulously in their astronomical records, noting its position in what we call the constellation Taurus, its brightness compared to Venus and the Moon, its color, and how long it remained visible. They watched it for nearly 2 years as it slowly faded, dimming from a brilliant point, visible in daylight, to a faint star barely visible to the naked eye, and finally disappearing entirely. What they witnessed was an explosion that had actually occurred around the year 4940, 6 BCE, more than 6,000 years earlier. The light from that explosion traveled through space for 65 centuries before reaching Earth in 1050 4CE. The star had been dead for 6.5 millennia, but its light was only just arriving. Today, we can see the remnant of that explosion through telescopes. We call it the Crab Nebula, an expanding cloud of debris, approximately 11 light-years across, still growing at 1,500 kilometers per second econd. At the center of the Crab Nebula, we can detect a pulsar, a rapidly spinning neutron star, rotating 30 times per second econd. The collapsed core that survived the explosion. The Crab pulsar is a cosmic lighthouse, spinning so fast that it completes 30 full rotations in the time it takes you to blink. It has powerful magnetic fields extending from its poles, and these magnetic fields emit beams of radiation, mostly radio waves and X-rays. As the neutron star rotates, these beams sweep across space, like lighthouse beams sweeping across the ocean. When the beams happen to point toward Earth, we detect pulses of radiation, regular as clockwork, 30 pulses every second, a cosmic heartbeat that has been ticking for nearly 1,000 years and will continue for thousands or millions more. The expansion of the Crab Nebula continues even now. Nearly a millennium after the light of the supernova faded from Earth's skies, the debris plows into the surrounding interstellar medium, the thin gas and dust that fills the space between stars, sweeping it up, compressing it, heating it. The collision creates a shock wave at the edge of the expanding nebula, and this shock wave triggers chemical reactions, excites atoms to emit light, and in some cases compresses nearby clouds of gas enough to trigger gravitational collapse, initiating the formation of new stars. This is one of the most important legacies of supernovae. They don't just create heavy elements, they also trigger star formation, compressing molecular clouds that might otherwise remain stable for millions of years, pushing them past the threshold where gravity takes over and collapse begins. The shock wave from a supernova can trigger the birth of dozens or hundreds of new stars. In this way, stellar death directly causes stellar birth. The ending of one star creates the conditions for the beginning of many others. The debris of the supernova, enriched with all the elements created during the star's life and in the explosion itself, gradually mixes with the interstellar medium. Over millions of years, the supernova remnant expands, fades, and eventually becomes indistinguishable from the general background of interstellar gas and dust. But the enrichment persists. The heavy elements scattered by the supernova remain, available to be incorporated into future generations of stars and planets. Our solar system formed from just such enriched material. The cloud of gas and dust that collapsed to form the Sunday and planets, about 4.5 billion years ago, had already been enriched by multiple previous generations of stellar death. The carbon and oxygen and silicon that make up the bulk of Earth's rocky mass, the iron and nickel in Earth's core, the nitrogen in our atmosphere, the phosphorus in our DNA, the calcium in our bones. All of these elements came from stars that died before our solar system existed. We are, quite literally, made from the ashes of dead stars, our very existence proof that death is creative, that endings enable beginnings. Let's consider now what remains at the center of the supernova, at the site where the core collapsed. The answer depends on the mass of the core at the moment of collapse. If the core's mass is between approximately 1.4 and 3 times the mass of the Sunday, what remains is a neutron star. If the core's mass exceeds roughly 3 solar masses, even neutron degeneracy pressure cannot halt the collapse, and the core continues contracting, passing through nuclear density and collapsing into a black hole. Neutron stars are objects so extreme, so far outside everyday experience, that they challenge our ability to comprehend them. Imagine the mass of the Sunday, or more than the mass of the Sunday, compressed into a sphere only 20 kilometers across, roughly the size of a large city. The entire mass of a star, squeezed into an object you could drive across in 20 minutes at highway speeds. The density is approximately 400 million billion kilograms per cubic meter, the same density as an atomic nucleus. At this density, matter exists in a state that has no terrestrial equivalent. The neutrons are packed together as tightly as quantum mechanics allows, touching each other, forming what physicists call degenerate matter. The gravitational field at the surface is so intense that if you could somehow stand on a neutron star, impossible as that would be, you would weigh billions of times more than you do on Earth. The escape velocity, the speed needed to leave the surface and reach space, is approximately 1/3 the speed of light, about 100,000 kilometers per second econd. If you dropped something onto a neutron star from a height, it would accelerate so quickly under the intense gravity that by the time it hit the surface, it would be moving at a significant fraction of the speed of light. The impact would release energy equivalent to a nuclear explosion. NASA scientists have calculated that if you dropped a marshmallow onto a neutron star from a few meters above the surface, the marshmallow would strike with the energy of 1,000 hydrogen bombs. The neutron star's gravity would compress it during the fall, squeezing it smaller and smaller, until it was just a thin stream of atoms moving at relativistic velocities. Neutron stars spin rapidly, typically completing hundreds of rotations per second econd, sometimes more. This rapid rotation is a direct consequence of the conservation of angular momentum. The original star before collapse was rotating, perhaps taking days or weeks to complete one rotation. When the core collapsed and shrank by a factor of thousands in radius, the rotation rate increased by a factor of millions, just as a figure skater spins faster when they pull their arms in close to their body. The fastest known pulsar, designated PSR J 1748 to 2446 AD, rotates 716 times per second econd, completing more than 42,000 revolutions every minute. The surface of this neutron star is moving at approximately 1/4 the speed of light. Many neutron stars are magnetars, possessing magnetic fields that are the strongest in the known universe, hundreds of millions or even billions of times stronger than the most powerful magnets ever created by humans. These magnetic fields are so intense that they warp the vacuum of space itself, creating bizarre quantum mechanical effects. When a magnetar has an outburst, releasing magnetic energy in a sudden violent event, it can briefly become the brightest X-ray source in the sky, visible across the entire galaxy, despite being only 20 kilometers across. The magnetic fields of neutron stars create beams of radiation emanating from the magnetic poles. As the neutron star rotates, these beams sweep across space like lighthouse beams. If Earth happens to lie in the path of one of these beams, we detect regular pulses of radiation, usually radio waves or X-rays, arriving with incredible regularity. These are pulsars, and they serve as some of the most accurate clocks in the universe. The Crab pulsar's 30 pulses per second econd are so regular that they can be used to test theories of gravity and detect gravitational waves. The recent confirmation in 2024 of a neutron star at the center of SN 1987A was a significant moment for astronomy. For 37 years, since the supernova was first observed in February 1980, 7 astronomers had been searching for the neutron star they predicted should exist at the remnant's heart. But the expanding debris was too bright, too thick with dust and gas, obscuring the center. Using the infrared capabilities of the James Webb Space Telescope, which can peer through dust that blocks visible light, astronomers finally detected evidence of the neutron star's presence, validating decades of theoretical work. This discovery matters because it confirms that our understanding of stellar death is fundamentally correct. We predicted that a massive star collapsing should leave behind either a neutron star or a black hole. We predicted the mass ranges for each outcome. We predicted the properties these objects should have. And now, watching SN 1987 evolve over nearly 4 decades, we've confirmed these predictions. The universe operates according to comprehensible physical laws, and we've learned to read those laws to predict outcomes, to understand processes happening at scales of energy and violence that dwarf anything in human experience. But neutron stars are not the only possible outcome of stellar core collapse. If the core is more massive, exceeding approximately 3 times the mass of the Sunday, then even the mighty neutron degeneracy pressure is insufficient to halt the collapse. The core continues to contract, compressing past nuclear density, and at a certain point, something remarkable happens. The escape velocity at the surface exceeds the speed of light. Nothing can escape, not even light itself. The collapsing core has become a black hole. A black hole is not an object in the conventional sense. It's a region of space-time where gravity has become so intense that the very fabric of space and time is warped beyond recognition. The matter that collapsed to form the black hole has fallen past the event horizon, the boundary beyond which escape is impossible, and continued falling toward the singularity at the center, a point of infinite density where the known laws of physics break down and our equations produce nonsensical infinities. We cannot see past the event horizon. No information can come out. The light emitted by matter, falling toward the event horizon, becomes increasingly redshifted, stretched to longer and longer wavelengths by the intense gravitational field until it fades into darkness. From the outside, we would see matter falling toward the black hole appear to slow down, to freeze at the event horizon. But from the perspective of the infalling matter, Therese no pause, no hesitation. It crosses the event horizon and continues falling, doomed to reach the singularity in a finite amount of proper time. Black holes are characterized by just a few properties: mass, spin, and electric charge. Everything else, all the details about what fell in, the specific atoms and molecules and structures, is lost. A black hole formed from the collapse of a stellar core is indistinguishable from one formed by any other means, as long as they have the same mass, spin, and charge. This has led physicists to say that black holes have no hair, meaning no other distinguishing features. But black holes are not entirely dark. Matter falling toward a black hole forms an accretion disk, a swirling vortex of superheated gas, orbiting the black hole before spiraling inward past the event horizon. The friction in the accretion disk heats the gas to millions of degrees, hot enough to emit X-rays. Some black holes launch jets from their poles, beams of particles and energy, extending for thousands or millions of light years, powered by the rotational energy of the black hole itself, through processes we still don't fully understand. We've detected stellar, mass black holes throughout our galaxy, usually in binary systems where we can see the effects of the black hole's gravity on a companion star. We've measured the masses of many of these black holes, confirming that they fall in the range predicted by theory, typically between 5 and 20 times the mass of the Sunday. And in 2015, the LIGO gravitational wave detectors made the first direct observation of two black holes merging, creating ripples in space-time itself that traveled across more than 1 billion light-years before reaching Earth, confirming Einstein's prediction about gravitational waves made a century earlier. Whether the core becomes a neutron star or a black hole, the supernova explosion itself scatters the star's outer layers into space. This expanding cloud of debris, the supernova remnant, continues to evolve for thousands or millions of years. The Crab Nebula, nearly 1,000 years old, is a young supernova remnant, still bright, still expanding rapidly. Cassiopeia, a remnant of a supernova that exploded about 350 years ago, shows beautiful, complex structures in X-ray and radio images, the debris expanding asymmetrically, revealing that the explosion itself was not perfectly spherical. These remnants are active sites of cosmic physics and chemistry, The expanding shock wave compresses the interstellar medium, triggering star formation in nearby molecular clouds. The shock accelerates particles to tremendous energies, creating cosmic rays, high-energy protons, and atomic nuclei that zip through space at nearly the speed of light. When these cosmic rays eventually strike Earth's atmosphere, they create showers of secondary particles. Some of these particles pass right through your body as you rest here. They're travelers from ancient supernovae, particles accelerated thousands or millions of years ago in stellar explosions, now completing their long journeys by passing through you, connecting you physically to events that happened before human civilization began. The heavy elements in the supernova remnant, the carbon and oxygen and silicon and iron and gold, all created in the star's life and death, gradually mix with the surrounding interstellar gas. Over millions of years, the remnant expands, cools, fades, and eventually becomes indistinguishable from the general background, but the chemical enrichment persists. The gas is now richer in heavy elements than it was before. When new stars form from this enriched gas, they will have planets, rocky planets, with iron cores and silicon mantles, atmospheres with nitrogen and oxygen, oceans with dissolved minerals, and perhaps, eventually, life built from carbon and nitrogen and phosphorus, life made possible by stellar death. As you rest here, perhaps feeling even more deeply relaxed, now the weight of your body fully supported, your breathing slow and steady, let's turn our attention from these cosmic processes to something closer, more immediate, more personal. We've witnessed the death of stars, the transformation of matter, the creation of elements, the persistence of influence, long after the original structure has dispersed. Now let's explore what these stellar deaths might teach us about our own experiences with endings, with loss, with the inevitable transformations we all face in our human lives. In our culture, we have a word that appears constantly when people discuss grief. When relationships end, when chapters of life close, the word is closure. It sounds clean, definitive, final. Closure suggests that to read a door we can shut, a book we can close, a definitive endpoint where the ending is complete and we can move forward without looking back. When someone we love dies, when a relationship that defined us ends, when we lose something that mattered deeply, we're often told we need closure, that we need to achieve resolution, that we should reach a point where we're finished with our grief and ready to move on. But here is a truth that researchers who study grief and loss have discovered through decades of careful observation and analysis. Closure in the sense of a complete resolution, a final ending to our emotional connection with what we've lost, doesn't actually exist. It's a myth, a cultural fiction that misunderstands how human beings actually process loss and maintain connections over time. And this myth isn't harmless. When we believe we should reach closure, when we expect our grief to have a clear endpoint, when we think there is something wrong with us if we're still affected by a loss years later, we're setting ourselves up for unnecessary suffering. Dr. Pauline Boss, a family therapist and researcher who has spent decades studying what she calls ambiguous loss, has written extensively about the problems with our cultural obsession with closure. Her research shows that, for many types of loss, particularly those that are unclear or unresolved, the goal of reaching closure is not just unrealistic, but actively harmful. when we believe we should achieve closure and then find ourselves unable to do so. We begin to think something's wrong with us, that we're failing at grief, that we're somehow broken or unable to heal properly. But the truth is that grief doesn't have an endpoint. Love doesn't have an endpoint. The connections we form, the relationships that shape us, the experiences that define who we are, these don't simply cease when external circumstances change. When someone we love dies, the physical relationship ends. We can no longer call them, touch them, share new experiences with them. But the emotional connection, the influence they had on us, the love we feel for them, none of that stops. It transforms, continues, persists in new forms. This is remarkably similar to what we've been exploring with stellar death, isn't it? The star as it was, the organized nuclear furnace, burning hydrogen and maintaining equilibrium for millions of years, that ends. The star explodes, disperses, transforms. But the star's elements, its creations, its influence on the surrounding space, all of that continues. The atoms that were once part of the star go on to become parts of new structures. The heavy elements it created enable future complexity. The shock wave triggers new star formation. The star persists through what it created and scattered, transformed but not gone, ended but continuing. Recent research on grief has revealed that the process is not linear, not a straight path from pain to resolution. Elizabeth K. Fabler, Ross's famous 5 stages of grief, denial, anger, bargaining, depression, acceptance, were never meant to be a rigid sequence everyone follows in order, though they're often misunderstood that way. More recent work by researchers like George Bonanno at Columbia University has shown that grief is actually oscillating, moving back and forth between different states, with no pressure or expectation to reach a final stage and stay there. The dual process model of grief, developed by Margaret Strobie and Henk Schut in the Netherlands, describes this oscillation beautifully and accurately. According to their research, people dealing with loss move back and forth between what they call loss-oriented coping, where the focus is on the loss itself, on processing the pain, on dwelling with what's gone, and restoration-oriented coping, where the focus shifts to adapting to life after the loss, building new patterns, engaging with changed circumstances, looking toward the future, and crucially, people also sometimes take breaks from both modes, distracting themselves, allowing moments of respite from the work of grieving, engaging in activities that have nothing to do with the loss. This back and forth movement is healthy. It's not a sign of failure or inability to let go. It's the natural way human beings integrate major losses into their ongoing lives. We move toward the pain for a while, processing it, feeling it fully. Then we move away from it, focusing on practical matters, on new relationships, on changed routines. Then we move toward it again, perhaps triggered by a memory, or an anniversary, or a moment that unexpectedly brings the loss rushing back. Over time, if the grieving process proceeds healthily, the intensity of the pain decreases. The oscillations become gentler, but they never completely stop. We don't reach a point where we're finished with the loss. We reach a point where we can carry it more lightly, where it's integrated into who we are, rather than overwhelming us. This is especially true with what Dr. Boss calls ambiguous loss. Situations where there is no clear resolution, no definitive ending, no closure in the traditional sense. When someone goes missing and we don't know if they're alive or dead. When a loved one has dementia and is psychologically absent but physically present. When a relationship ends without explanation or clear communication. When we're forced to leave our homeland and don't know if we'll ever return. When we lose a job suddenly and without understanding why. These are losses without clear boundaries, endings that remain open, situations that don't resolve neatly. And the truth is, ambiguous loss is far more common than we often acknowledge. So much of life involves uncertainty, situations that don't resolve clearly, endings that remain somehow incomplete. We live with these ambiguities constantly, whether we acknowledge them or not. Someone we cared about drifts out of our life without a clear goodbye. A project we invested in ends inconclusively. A hope we held fades without a definitive moment when we can say it's truly gone. Life is messier than our desire for closure would prefer, with ambiguous loss. Dr. Boss argues, the therapeutic goal must shift from achieving closure to finding meaning. We can't close the book on something that's still ambiguous, still unresolved, still uncertain. But we can find ways to live with the ambiguity, to make meaning despite the uncertainty, to accept that some questions won't be answered, and some endings won't be clean. This requires a different kind of psychological work than striving for closure. It requires cultivating what Boss calls tolerance for ambiguity, developing the capacity to sit with uncertainty, to hold multiple possibilities simultaneously, to accept that we can't control everything, and that life often resists neat resolution. Think about the supernova remnant we discussed earlier. The expanding cloud of debris from an exploded star. Is it finished? Has it reached its endpoint? In one sense, yes, the explosion is over. The star has died. The violent release of energy happened long ago, but the remnant is still expanding, still evolving, still interacting with its environment, still changing. It will continue expanding for thousands or millions of years. There is no moment when we can point to it and say, now it's complete. Now the process is finished. The process is the ongoing expansion, the continuing dispersal, the gradual integration with the surrounding medium. The ending was just a transition to a different kind of existence, a different kind of ongoing change. Similarly, when we experience major loss in our lives, we don't reach a point where it's finished, where we're done, where we've achieved closure. We reach a point where we're in a different relationship with the loss. The acute pain softens into something more like a persistent ache, which softens further into occasional twinges, which eventually becomes a kind of bittersweet tenderness when we remember. But we don't stop remembering. Most of us don't want to stop. The memories, even the painful ones, are precious because they connect us to what mattered, to who we were, to relationships and experiences that shaped us. This is what psychologists and grief researchers call continuing bonds. The recognition that our relationships with people we've lost don't end when they die or when we're separated from them. Instead, these relationships transform. We carry the person with us, internalized, part of our psychological landscape. We might have conversations with them in our minds. Imagine what they would say about situations we're facing. Feel their presence in moments of decision or difficulty. Act in ways they taught us to act. value things they taught us to value. This isn't pathological. It's not an inability to let go or move on. It's a healthy adaptation that allows us to maintain connection while acknowledging the reality of physical absence or changed circumstances. Sigmund Freud, the founder of psychoanalysis, lost his beloved daughter Sophie to illness in 1920. She was only 27 years old. Freud was devastated. For the rest of his life, he wore a locket with her picture on his watch chain, keeping her close to his heart. When people asked about his grief, he would point to the locket and say simply, "She is here." He never got over her death in the sense of reaching closure or moving on. Instead, he found a way to carry her with him, to maintain the bond while living his life, to acknowledge that she was both gone and still present, absent physically but continuing through his love and memory. This is what most people who experience significant loss actually do. Whether consciously or not, we don't sever the connections, we transform them. We find ways to carry forward what mattered. The person who died, or the relationship that ended, or the life chapter that closed, continues to influence us, shape us, affect our choices and values and understanding of ourselves. This isn't failure to achieve closure. This is the reality of how human connection and identity actually work. But our cultural obsession with closure can make this natural process harder. When well-meaning friends or family members tell us we should be over it by now, when we read advice suggesting we need to let go and move on, when we ourselves feel guilty for still grieving months or years after a loss, we're fighting against the natural process of integration. We're trying to force an ending that isn't real, that can't be real for something that genuinely mattered to us. Perhaps we can learn something from the universe's approach to endings. Stars don't fight their deaths. They don't try to maintain fusion past the point when it's sustainable. When the iron core forms and the star's fate is sealed, Therese, no resistance, no denial, no bargaining with the laws of physics. The star follows its nature, transforms according to the fundamental forces that govern it, and in doing so creates something new. Scatters elements that enable future complexity, triggers star formation through its shock wave. Now I'm not suggesting we should be passive in the face of loss, that we shouldn't grieve or struggle with our endings. Human consciousness gives us something stars don't have: the capacity for meaning, making, for emotion, for agency in how we respond to circumstances. We're not governed purely by physical laws. We have choice, creativity, the ability to find purpose in suffering, but there might be wisdom in accepting the inevitability of transformation, in recognizing that some changes can't be prevented or reversed, in understanding that endings will come, regardless of how much we wish they wouldn't, and that fighting against inevitable transformation often creates more suffering than the transformation itself. Therese also wisdom in recognizing that endings create possibilities. Every supernova scatters elements that were locked inside a star for millions of years, making them available for future generations of stars and planets. Every personal ending, as painful as it might be, creates space for something new. The job that ends might have been stifling growth we needed to experience. The relationship that dissolves might have been preventing us from becoming who we need to be. The life chapter that closes might have been keeping us from discovering new aspects of ourselves. This doesn't make the loss less real or less painful. Acknowledging that endings create possibilities isn't the same as saying the ending was good or welcome or wanted, but it does mean that the ending isn't purely destructive. It's transformative, and transformation, by its very nature, creates new possibilities that didn't exist before. In therapy and counseling, there's been a shift in recent decades toward what's called the termination as transformation perspective, moving away from the older termination as loss framework. Instead of viewing the end of therapy primarily as a loss, something to grieve, the newer perspective emphasizes it as an opportunity for growth, integration, internalization. The client takes what they've learned, internalizes the therapeutic relationship, carries it forward into their life as an internal resource they now possess. The relationship doesn't end in the sense of disappearing. It transforms into something internal, a capacity the person has developed, wisdom they've gained, ways of thinking about themselves that persist beyond the weekly therapy sessions. This applies to all kinds of endings in life. When a relationship ends, we don't lose everything we gained from it. We carry forward the growth, the lessons, the ways we were changed by loving and being loved. When a job ends or a life chapter closes, we take with us the skills we developed, the experiences we had, the person we became through that time. The external circumstances change, but what we internalized persists. What we became through the experience continues even though the experience itself is over. This is the difference between closure, which implies a door swinging shut and locking behind us, and transformation, which implies ongoing change and continuation in new forms. Closure suggests finality, completion, the end of influence. Transformation acknowledges that influence continues even as forms change, that what mattered persists even though circumstances are different, that we carry forward what shaped us even when the original source is gone. There's something in psychology called the peak end effect, discovered through research by Daniel Kahneman and others. It's the observation that when we remember experiences, we tend to focus disproportionately on the peak moments, the most intense points, whether positive or negative, and on the ending. How an experience ends significantly shapes how we remember and evaluate the entire experience, sometimes more than the totality of the experience itself. This can distort our perception. A relationship that ends badly might be remembered as bad overall, even if most of it was good. A project that finishes poorly might seem like a failure, even if the process was valuable and taught us important things. The ending colors everything that came before, sometimes unfairly. This suggests that creating good endings, to the extent we can, matters more than we might think. Not because endings are truly final, but precisely because they disproportionately influence memory and meaning. When we have the opportunity to shape an ending, to create a ritual, to say goodbye deliberately, to mark a transition with intention and care, we're doing important psychological work that will affect how we remember and make meaning of everything that came before. This is why funeral rituals exist in virtually every human culture across history, why graduations matter, why retirement ceremonies and going away parties and divorce rituals in some traditions are important. These aren't just social niceties. They're acknowledgments that endings are significant, that transitions from one state to another deserve recognition and marking, that the passage from what was to what will be should be honored rather than ignored or rushed through. Not because the ending is final, but precisely because it isn't. Because what's ending will continue in transformed ways. And the ritual helps us begin that transformation consciously, rather than stumbling through it in confusion. The ritual creates a psychological milestone, a marker in memory, a point we can look back to and say, that's when things changed. For those of you listening who are dealing with grief or loss right now, or who've experienced significant endings and are still processing them, perhaps Therese comfort in this perspective. You don't have to reach closure. You don't have to be finished with your grief. You don't have to move on in the sense of leaving something behind completely and never thinking about it again. That's not how human beings actually work. And expecting yourself to achieve that kind of closure is setting yourself up for unnecessary self-judgment. Instead, you can work toward integration, toward transformation, toward finding ways to carry what matters forward while acknowledging that the old form is gone. You can oscillate between remembering and living in the present, between honoring what was and building what will be. You can maintain bonds with what you've lost while forming new bonds. You can find meaning in the absence of closure, recognizing that some things remain ambiguous, unresolved, open-ended, and that's okay. That's part of being human. That's how life actually is, not how we wish it would be or how self-help books tell us it should be. And you can recognize yourself as part of a cosmic pattern of transformation, just as stars don't truly die but transform, dispersing their creations across space and influencing vast regions around them. For millions of years, you don't simply end things. You transform them, carry them forward in new forms, continue to be influenced by what seemed to be finished. Your lost loved ones live on in your memories, in the ways they changed you, in the values or habits or perspectives you internalized from them. Your ended relationships or finished life chapters continue through what you learned, who you became, how you were shaped by them. This is the real legacy, the real continuation, not the fantasy of closure where everything resolves neatly, and we can package it up and put it away. But the reality of transformation where what mattered persists in new forms, where influence ripples outward long after the original source has changed, where endings are revealed to be transitions rather than terminations. Now let's return to the cosmic perspective, to the big picture that holds all of this. Carl Sagan, the astronomer and science communicator, who did more than perhaps anyone to make cosmic perspective accessible to ordinary people, famously said during his television series Cosmos in 1980, "We are made of star stuff." The phrase captured the public imagination, appearing on posters and t-shirts, quoted in books and articles, becoming part of popular culture. But what does it actually mean, and why does it matter? Sagan was stating a literal scientific fact, not a poetic metaphor. Every atom in your body heavier than hydrogen was forged in the core of a star or in a supernova explosion. The nitrogen in your DNA, the calcium in your bones and teeth, the iron in your blood, the carbon in your cells, the oxygen you're breathing right now, all of these elements were created through stellar nucleosynthesis, the nuclear fusion reactions happening in the cores of dying stars and in the shock waves of supernova explosions. The first generation of stars, born from the primordial hydrogen and helium created in the Big Bang, could fuse elements up to iron in their cores. But when they exploded as supernovae, they scattered those elements into space, enriching the interstellar medium. The second generation of stars formed from gas that already contained carbon, oxygen, silicon, iron. These stars could create even more heavy elements, and when they died, they further enriched the cosmos. Our Sunday is a third or fourth generation star, maybe even later, formed from gas that had been cycled through multiple generations of stellar death and birth. This means the elements that make you possible only exist because massive stars lived, died, and scattered their creations across space billions of years ago. The supernova explosions we've been discussing tonight aren't just distant astronomical events. They're your origin story. Without stellar death, without these violent transformations and dispersals, you couldn't exist. Not metaphorically, literally. There would be no heavy elements to make rocky planets, no oxygen to breathe, no carbon to build organic molecules, no calcium for bones, no iron for blood. You are the continuation of stellar death. You are what stars become when they die, and their elements recombine in new patterns billions of years later. Their endings made your beginning possible. This realization can feel either diminishing or elevating, depending on how we hold it. On one hand, it might seem to make us small, insignificant. We're just temporary arrangements of atoms, brief patterns in the endless transformation of matter and energy flowing through the universe. On cosmic scales of space and time, our individual lives are vanishingly brief, less than a heartbeat in the multi-billion-year lifetime of the universe. What can our small concerns possibly matter against this vast backdrop? But Sagan and others who've contemplated the cosmic perspective argue the opposite. The fact that we're made of star stuff makes us precious, not insignificant. As Sagan wrote, every one of us is, in the cosmic perspective, precious. If a human disagrees with you, let him live. In 100 billion galaxies, you will not find another. You are unique. Your particular arrangement of atoms, your specific configuration of star stuff has never existed before and will never exist again. You're the result of 13.8 billion years of cosmic evolution, of countless stellar deaths and births, of the formation of our solar system and Earth, of billions of years of biological evolution, of the incredibly improbable circumstances that brought your parents together and resulted in your existence. The odds against your existence are astronomical, literally incalculable. And yet, here you are, not just existing but conscious, aware, able to contemplate your own existence and the nature of the universe that created you. You're made of atoms that were forged in stellar cores, and those atoms are now arranged in such a way that they can understand where they came from. You are the universe knowing itself. The cosmos become conscious and self-aware, matter organized in patterns complex enough to wonder about matter. This is remarkable. This is profound. This is, in its way, miraculous. Even if it happened through natural processes, we can study and understand, rather than supernatural intervention. The fact that the universe can produce beings who can understand the universe, that stars can create elements that eventually arrange themselves into patterns, capable of comprehending stars. This is extraordinary. The cosmic perspective doesn't diminish us. It connects us. It shows us that we're not alien to the universe, not separate from nature, not observers standing outside creation, looking in from some privileged position. We're integral parts of the whole, participants in the ongoing story of cosmic evolution, made from the same matter and governed by the same laws as everything else that exists. When you look up at the night sky, you're not looking at something foreign or distant. You're looking at your origins, at the processes that made you possible, at your extended family scattered across the cosmos. The stars aren't separate from you. They're your ancestors, in a very real sense. The atoms in your body have been parts of countless other structures before becoming part of you. Mountains, oceans, clouds, plants, animals, other humans, all have contained atoms that are now part of you. And after you die, those atoms will become parts of countless future structures. Some will become parts of soil, enriching the earth. Some will become parts of plants, then animals, then perhaps other humans. Some will be released into the atmosphere, dispersing widely. Eventually, billions of years in the future, when our Sunday expands into a red giant and dies, some of the atoms that were once part of you might be dispersed back into space, available to become parts of new stars, new planets, perhaps new life forms in the distant future. You are part of a cycle that has no beginning and no end, just continuous transformation. Before you existed, the atoms that make you up were parts of countless other structures, participants in countless other stories. And after you're gone, those atoms will participate in countless future stories. You're a temporary eddy in the river of matter and energy flowing through the cosmos. A brief but meaningful pattern in the endless transformation. This doesn't make your life meaningless. It makes it connected, continuous with everything that is. Your existence is not separate from the existence of stars. It's a direct consequence of stellar processes. Every breath you take, every thought you think, every emotion you feel, every choice you make, all of this is made possible by the violent deaths of massive stars billions of years ago. And your influence, like the influence of those dead stars, will continue long after you're gone. The people you've touched will carry your influence forward. The changes you've made in the world, large or small, will ripple outward. The love you've given will persist in those you've loved. You'll continue through what you've created, what you've taught, what you've shared, what you've been to others. Just as the dead stars continue through the elements they scattered and the new stars and planets their deaths enabled. There is also something profound in recognizing that we're all made of the same stuff. Literally, every human being, every animal, every plant, every rock, every planet and star, all of it is made of the same fundamental particles arranged in different configurations. We're not separate species or separate kingdoms, or separate anything at a fundamental level. We're all star stuff, all part of the same cosmic process of transformation, all temporary patterns in the flow of matter and energy through space and time. This realization can foster compassion, connection, a sense of kinship with all existence. The person who disagrees with you, who frustrates you, who seems so different from you, is made of the same atoms you are, atoms that came from the same stellar deaths, atoms that are equally temporary and equally precious. We're all riding the same cosmic wave together, all brief expressions of the universe's creativity, all meaningful despite our brevity, all connected despite our apparent separation. As we near the end of this journey together, I want to invite you to take a moment to feel your place in this vast cosmic story. Feel the weight of your body, the result of gravity, the same fundamental force that collapses stellar cores and creates black holes. Feel your breath. Oxygen atoms fused in red giant stars, billions of years ago, now cycling through your lungs, enabling your metabolism, making consciousness possible. Feel your heartbeat. Iron atoms created in supernova explosions, now dissolved in your blood, carrying oxygen to every cell in your body, keeping you alive. You are ancient and you are new. Ancient because every atom in you is billions of years old, forged in stellar furnaces that no longer exist, recycled through countless forms before becoming part of you. New because this particular arrangement, this specific configuration that is uniquely you, has never existed before in all the 13.8 billion years of cosmic history. You're both a continuation of everything that came before and a completely novel creation, unprecedented and irreplaceable. The endings you've experienced in your life, the losses, the transformations, the moments when something you relied on changed or disappeared. These are all part of this larger pattern. Just as stars must die for new stars to form, just as supernovae must scatter elements for planets and life to arise, the endings in your life create space for new beginnings, new possibilities, new chapters you couldn't have imagined while clinging to what was. They're not just losses, though they are that too. They're also transformations, necessary transitions, creative destructions that clear the way for new growth. This doesn't make them less painful. Acknowledging that endings serve a purpose doesn't erase the grief of losing what mattered, but it does place that grief in a larger context, a cosmic pattern where transformation, rather than permanence, is the fundamental nature of reality. You don't have to reach closure with your losses. You don't have to finish your grief or complete your process of letting go or move on, in the sense of leaving something behind forever. You can carry what matters forward, transformed but persistent, integrated into who you've become. You can oscillate between remembering and living in the present, between honoring what was and building what will be. You can find meaning in the midst of ambiguity and transformation in the midst of endings. And you can rest in the knowledge that you're part of something vast and beautiful, a cosmic cycle of death and rebirth that has been continuing for billions of years and will continue for billions more. You're made of stars. You're made of supernovae. You're made of the universe's creative violence and patient accumulation, its tendency toward complexity, and its willingness to destroy complexity when the time comes. Its endless transformation and its persistence through transformation. When your particular configuration disperses, when you undergo your own transformation and return to the cycle, your atoms will be available to become parts of new structures, new stories, new possibilities. The love you gave will continue in those you loved. The person you were will continue in those you influenced. The changes you made will continue rippling outward, effects spreading beyond your ability to see or measure them. The stars teach us this lesson with perfect clarity. They live, they die, they transform, and through their deaths, they make new life possible. They don't resist the inevitable. They follow their nature, burn through their fuel, collapse when they must, explode when they must, and in doing so, create beauty, possibility. The conditions for consciousness itself to arise billions of years later, perhaps we can learn to do the same, to accept our own transformations with grace, to recognize that endings are not failures but necessary transitions, to trust that what we create and what we give will continue long after the particular form we currently inhabit has dispersed back into the cosmic flow. Thank you for joining me on this journey through stellar death and human transformation, through the physics of supernovae and the psychology of endings, through cosmic perspective and personal meaning. If you found peace or insight or companionship in this exploration, I encourage you to like this video and subscribe to Gentle Sleep ASMR. Your support allows us to continue creating these meditative explorations, where science meets the soul, where cosmic wonders become doorways to self-understanding, where the vastness of the universe reveals our preciousness rather than our insignificance. Rest well tonight. Dear listener, you are made of stars, ancient atoms arranged in a pattern that has never existed before and will never exist again. You carry within you the creative power of the universe, the legacy of countless stellar deaths, the potential for influence that extends far beyond your brief lifetime. May you find peace with your endings, knowing their transformations. May you carry forward what matters, integrated and persistent. And may you rest in the knowledge that you're part of an ancient, ongoing story of cosmic evolution, brief but precious, temporary but meaningful, unique and irreplaceable in the vast expanse of space and time. Sleep well,